Okay, welcome to another episode of Probability and Statistics. We're continuing solving questions about statistics, and I have yet another question. The question is as follows. A structural engineer conducted an experiment and recorded a failure strength of 12 samples of a certain material produced. The standard deviation of the measurements is given by 989 kilonewton, and it's known that the failure strengths are normally distributed with mean 3000 kilonewton. So that is the mean of the population for this type of material. What is the likelihood of the mean failure strength of any 12 samples being lower than 2000 kilonewton? Remember that it's asking mean failure strength, so we're basically interested in the x-bar, which is the sample mean, and we're trying to specifically looking for the probability this x-bar is smaller than 2000 kilonewton. That's our question, in fact. I want to remind you a couple of things. First of all, that it is 12 samples, so remember that we have a rule of thumb. If there are two conditions, if we have 12 samples, which is less than 25, that is our first condition. So number of samples must be smaller than 25. The second condition is that we need to have the population variance unknown. So if these two conditions are satisfied, then we have we can assume that the distribution of x bar is t. So the t distribution assumption here is more valid compared to a Gaussian or normal assumption. So in this case, we need to use a t distribution with 11 degrees of freedom because we've got 12 samples, so we basically subtract 1. So in that case, we need to use a t distribution with 11 degrees of freedom. Okay? That's our first observation. So let's continue. We have another test statistic, this t, or another random variable t. So we're basically transforming the random variable x bar by assuming that it's t distributed. It's 2000 minus mu, which is in our case, as you know, the population mean divided by s over square root of n. I just wanted to write it using letters so that I can replace them later. So this probability is given by pt, smaller than 2000. Minus mu is given by 3000, okay, because it's assumed to be normally distributed 3000 kilonewtons, so it's basically plug-in value here, and then s is given by 989 divided by square root of 12. So if you do the math, you will realize that this is probability t smaller than minus 3.5. So it's not a big calculation here, so it's quite straightforward. One of the things that you can realize that it's easy to get to here, but then it's our now ability to use the t distribution table, right? So using a t table or t distribution table, we basically have to go to 11 degrees of freedom. Okay? So that's one of the crucial points here. And I realize that if you look at the table with 11 degrees of freedom, I realize that 3.5 is greater than 3.106. That's the maximum I can find in that table, in that particular row, that satisfies this inequality. So which is given by this 3.106 corresponds to t 0.005. Okay, that observation is really critical. You can also figure out that t 0.01 also satisfies this condition, but that is the one that is maximized. Okay, so it's the maximum value that satisfies this. So I took this value, as you might realize that the t table does not have all the possible probability values. So we're choosing the one that fits our needs best. So in our case, we can conclude that pt smaller than 3.5 can be upper bounded by 0.005 because of this inequality. Okay.